Ever tried to have your cake and eat it too? I mean, who hasn't? But using data without actually seeing it, that's a whole other level of impossible. And that's what we're diving into today, this whole world of privacy-preserving computation.
You, our listeners, you've sent us some seriously cool stuff on this, by the way. Seems like you as fascinated by this as we are.
Yeah, it's pretty mind-blowing stuff when you really think about it. We're talking about tools and techniques that let us, well, kind of like extract meaning and value from data without ever actually exposing the raw information itself. It's
Yeah.
like imagine trying to understand the essence of a painting without ever actually seeing the painting itself.
Okay, I like where you're going with that, kind of like analyzing the brush strokes and the colors through, I don't know, some kind of special filter. Exactly, you're getting the idea. So we're talking about things like homomorphic encryption, differential privacy, Shamir's secret sharing, and get this, zero knowledge proofs.
Zero knowledge proofs. Okay, that one sounds like it's straight out of a spy movie. I'm hooked already.
Yeah, it does, doesn't it? And in a way, it kind of is. We're talking about being able to prove something is true without revealing the actual information that makes it true. It's like, how do you even...
Okay, now you have to explain that one. My brain just did a backflip. But before we get ahead of ourselves, let's rewind a bit. What are we really talking about here? What even is privacy-preserving computation?
You got it. Let's
Yeah.
break it down. So, at its core, privacy preserving computation is all about, well, preserving privacy while still being able to do things with data. It's about finding ways to analyze, share, and use information without compromising its confidentiality.
Okay, so it's like having a super secure lockbox for your data. You can still use the data inside for things like analysis or calculations, but no one can actually see the raw data itself, right?
Exactly. That's a great way to put it. And that's where these different techniques we mentioned come in. They offer different ways to achieve this kind of secure computation. They're like different tools in a toolbox, each with its own strengths and weaknesses.
Okay, now I'm really intrigued. We've got this toolbox of privacy-preserving gadgets. Let's open it up and see how they work. So we've got this toolbox full of privacy-preserving gadgets ready to be explored. Where do we even begin?
Well, why don't we start with that super secure lockbox you mentioned earlier, homomorphic encryption. It's like the VIP of our privacy preserving party.
Homomorphic encryption.
Yeah.
Yeah, that one sounds seriously impressive. It's like you're telling me we can actually perform calculations on data without ever decrypting it. Like, how is that even possible?
I know, right? It sounds like something straight out of a sci-fi movie. But that's the beauty of it. Homomorphic encryption allows us to work on encrypted data as if it were plain text, all while keeping the underlying information completely hidden.
Okay, that's just mind-blowing. But the Wikipedia article you sent mentioned something about different levels of homomorphic encryption. What's that all about?
Ah, good point. It's not quite as simple as one size fits all when it comes to homomorphic encryption. We have different types, each with varying levels of flexibility in the computations you can perform on the encrypted data.
So it's like having different security clearances to access different parts of a facility.
Exactly. Think of partially homomorphic encryption as having limited access. You can
Mm.
perform certain basic operations like additions or multiplications, but you can't just go around opening every door.
Okay, I see. So partially homomorphic encryption is like having a key card that gets you into certain areas, but not others. What about this other one, fully homomorphic encryption? That sounds way more powerful.
It is. Fully homomorphic encryption is like having the master key. You can perform any computation on the encrypted data that you could on plain text data without ever needing to decrypt it. It's like having your cake and eating it too. You get the utility of the data without ever compromising its privacy.
Wow, that's incredibly powerful. But is this fully homomorphic stuff actually usable today? Or is it still just theoretical, like something we're still working on?
Well, that's the exciting part. While fully homomorphic encryption is still an active area of research, it's rapidly advancing. We're seeing breakthroughs all the time. And in fact, there are already practical applications emerging.
Really, like what can we actually do with fully homomorphic encryption today?
One promising area is in secure cloud computing. Imagine being able to upload your sensitive data to the cloud, have the cloud perform complex computations on it, like analyzing medical records or financial transactions, and get the results back without the cloud provider ever seeing your actual data.
Okay, now that's what I'm talking about. That's the kind of real-world impact that gets me fired up about this stuff. But cloud security is a whole other can of worms. It's like we're constantly playing catch-up with the hackers and cyber criminals out there.
It's a never-ending battle, that's for sure. But that's why these privacy-preserving technologies are so important. They give us new ways to fight back, to build more secure and trustworthy systems.
You know what's really cool about all this? It's not just some pie-in-the-sky idea. The Wikipedia article actually lists real-world software libraries like eLib and Microsoft Seal they're being developed to implement these homomorphic encryption concepts. It's like we're living in the future.
Absolutely. And it's just the tip of the iceberg. As these technologies mature, we can expect to see even more incredible applications emerge, applications that we can't even imagine right now.
Okay, so homomorphic encryption is all about working on encrypted data directly,
Yeah.
like performing surgery with those super sensitive gloves you mentioned earlier. What about that layer of fog technique, differential privacy? How does that one work its magic?
Ah, yes. Differential privacy. This one's all about adding a bit of calculated randomness to our data to protect individual privacy while still allowing for accurate statistical analysis. Think of it like adding a bit of blur to a photo.
Okay, I'm with you so far. Blur the photo so you can't make out individual faces, but you can still see the overall scene. But how do you actually add blur to data?
That's where the noise comes in. We strategically inject a tiny bit of random data noise into the dataset. It's like adding a sprinkle of static to a radio signal. This noise makes it much harder to identify individual data points, but still allows us to extract meaningful insights from the aggregate data.
So it's like trying to eavesdrop on a conversation in a crowded room. You might be able to pick up on the general topic, but you won't be able to hear every single word clearly.
Precisely. And the beauty of differential privacy is that this noise is carefully calibrated to ensure that the overall statistical properties of the data remain intact. We're not just randomly scrambling everything.
Okay, that makes sense. But if you're adding randomness to the data, doesn't that affect the accuracy of the results? I mean, if you're blurring a photo too much, you eventually lose all the details.
That's a great question, and it highlights a key trade-off in differential privacy, the balance between privacy and accuracy. It's a bit of a tightrope walk. The more noise we add, the stronger the privacy protection, but the less precise our results might be.
So it's about finding the sweet spot, enough noise to protect privacy, but not so much that the data becomes meaningless.
You got it. And that's where the skill and expertise of data scientists come in. They need to carefully determine the appropriate level of noise based on the specific data set and the desired level of privacy. It's a delicate balancing act.
That makes sense. So we've got homomorphic encryption, which lets us work directly on encrypted data, and differential privacy, which adds a layer of anonymity to our data sets. What's next in our privacy-preserving toolbox? Let's unlock Shamir's secret sharing, shall we?
Ah,
Okay, let's see. We got homomorphic encryption, which is like that super secure lockbox. And then there's differential privacy that's like adding that protective fog to make individuals unidentifiable. But now we're about to unlock Shamir's secret sharing. And this one, well, it sounds like it could be straight out of a spy movie.
it does, doesn't it? It's all about dividing a secret into multiple parts, and you need a certain number of these parts or shares to reconstruct the original secret. It's like a treasure map. But instead of marking an X on the spot, you've got to find all the pieces of the map first.
Okay, I'm kind of getting a national treasure vibe here. I'm in. But how does this actually work in the real world? What kind of secrets are we talking about here?
Well, the beauty of Shamir's secret sharing is that it's incredibly versatile. It can be used to protect anything that can be represented digitally, cryptographic keys, sensitive data, even the launch codes to a nuclear missile. Okay, maybe not that last one, but you get the idea. It's designed for high-stakes security.
Okay, now that's serious stuff.
Yeah.
But let's say we're talking about something a bit less, explosive. What about protecting sensitive information within a company? The Wikipedia article mentioned something about using this for access control. How would that work?
Imagine a company where multiple executives need to authorize a critical financial transaction. Instead of giving each executive the full authorization code, which would be risky if one of them, say, lost their laptop or, I don't know, wrote it down on a sticky note.
Which, let's be honest, we've all done at some point.
Exactly.
Yeah.
So instead of doing that, we use Shamir's secret sharing to split the authorization code into multiple shares, and we give each executive one share. To authorize the transaction, a certain number of executives need to come together, combine their shares, and reconstruct the full authorization code.
That's a pretty clever way to add an extra layer of security. It's like having those safety deposit boxes at the bank. You need two keys to open them. But the Wikipedia article also mentioned a potential downside to Shamir's secret sharing. What happens if one of those secret shares goes missing? Is the whole thing toast?
That's the trade-off with this technique. It's incredibly secure, but it's also unforgiving. If even one share is lost or destroyed, you can't reconstruct the original secret. It's like losing a piece of a jigsaw puzzle. Without all the pieces, you'll never see the full picture.
So it's a double-edged sword, super secure as long as everyone keeps track of their shares.
Exactly. It highlights the importance of secure storage and management of those secret shares. It's not something you want to leave on a sticky note on your computer monitor.
Noted. Okay, we've covered homomorphic encryption, differential privacy, and Shamir's secret sharing. That's 3 down, 1 to go. And it's the one that's been bugging me since the beginning, zero-knowledge proofs. I mean, the name itself sounds like a paradox. How can you prove you know something without actually revealing what you know?
It's like magic, isn't it? But it's really not about magic. It's about clever mathematics. Remember that example we talked about earlier with the cave and the magical door?
Oh, right. The one where you have to prove, the secret password to open the door without actually telling me the password.
Exactly. And that's the essence of a zero-knowledge proof. You're demonstrating that you possess certain knowledge without revealing the knowledge itself. It's like convincing someone you have a winning lottery ticket without showing them the actual numbers.
Okay, I think I'm starting to wrap my head around this. But the Wikipedia article mentions some pretty heady concepts like completeness, soundness, and even different types of zero knowledge. Are we about to go down a rabbit hole here?
Don't worry, I'll spare you the technical jargon. But yeah, there are different flavors of zero-knowledge proofs, each with its own level of security guarantees. But at their core, they all share this fundamental idea proving, something without revealing what you know. It's like the ultimate trust-building exercise.
Okay, so it's all about proving you have the keys to the kingdom without handing over the actual keys. I like it. But let's bring this back to the real world. What are some practical applications of these zero-knowledge proofs? Give me an example of where this stuff is actually being used today.
Well, one really cool application is in the world of cryptocurrencies, specifically with something called ZK snarks. Zero knowledge, succinct, non-interactive arguments of knowledge. Catchy name, right?
ZK what now? You lost me, it's succinct.
Basically, it's a way to verify transactions on a blockchain without revealing any of the sensitive information involved. Think about it right now. If you make a transaction on a public blockchain like Bitcoin, everyone can see your transaction details, right? How much you sent, where you sent it, it's all out there in the open.
Yeah, and that kind of defeats the whole purpose of privacy, doesn't it?
Exactly. But with ZK snarks, you can prove that your transaction is valid, that you have the funds, that you're not trying to double spend, all that good stuff, without revealing any of the transaction details. It's like being able to pay for your groceries without anyone knowing what you bought.
Okay, now that's what I'm talking about. Anonymous grocery shopping, finally. But seriously, this is some seriously next-level privacy tech.
It is, and that's just one example. Zero-knowledge proofs have the potential to revolutionize the way we think about privacy and security in countless domains. We're talking about everything from online voting and identity verification to secure data sharing and even building more trustworthy artificial intelligence systems.
Wow, that's pretty mind-blowing. We've gone from trying to have our cake and eat it too, to exploring a whole world of privacy-preserving possibilities, homomorphic encryption, differential privacy, Shamir's secret sharing, and these mind-bending zero-knowledge proofs. It's incredible to think that what might sound like science fiction is actually becoming a reality.
Absolutely. It's an incredibly exciting time to be working in this field. And the best part is that this is just the beginning. As these technologies continue to evolve, we can expect to see even more innovative applications emerge. Who knows what the future holds? But one thing's for sure, privacy-preserving computation is going to play a pivotal role in shaping our digital world for the better.
One thing that really struck me throughout our deep dive today is how important it is to be aware of these different privacy-enhancing technologies. It's not just about being a tech whiz, it's about being an informed citizen in a world where data is becoming increasingly central to our lives. So, to our listeners out there, keep asking questions, keep exploring, and keep demanding better protection for your information.
Well said. Knowledge is power, especially when it comes to protecting our privacy in this digital age.
This has been an awesome deep dive into the world of privacy-preserving computation. I'm walking away with my mind blown and a whole new appreciation for the power of keeping our data safe and secure. Thanks for joining us.